I have two examples for you when it comes to creating a recursive definition. The steps are overall the same, so I want to kind of use this as a template for my two examples I'm about to show you here. But things you're going to have to remember, as we've talked about this before, is make sure you understand what the base case is going to be and what the recursive case. The recursive case is really important because remember, it's got to fit a recursive call pattern. And I'll explain that here in a second once we get to this example, but remember the pattern that we're going to need in order to do this. You're going to be given an initial condition and then how to find the next value. So given a recursive function, a to the nth power for a is a all real number and a non-negative, and n is a positive integer. So I'm going to create a recursive function where a of n is non-zero, and then just translation from there, and then take care of the base or the initialization. So the base case is going to be a to the 0 equals 1. Now, how did I get away with that? Using 0 as our initial starting point, but anything to the power of 0 is still 1. So I still satisfy the condition that I have. So be very careful on how this is worded so you start correctly, because starting correctly obviously is pretty darn important here. Then after that, I want to start looking for a recursive pattern in the recursive case. What do I mean by that? Well, remember that I'm going to have one item constantly incrementing because that's our recursive setup. So let's see if we can figure out a pattern here. First we have 1, which remember, our base case can be a little bit different than everything else. Our a of 1 is going to be 1 times a. Then we have our a of power of 2, a times a. Power of 3 is a squared plus a. Now, right here, I know somebody's going to say, well, you could have done a times a, which is also true, but it's not recursive. Notice what's being highlighted here. Each one of those has some stabilizing factor where it's part of the recursive call, but then the recursive call has something that's incrementing or decrementing if we needed to in that portion of it. So we need to find a pattern for this overall setup in order for it to work. So that recursive pattern is really, really important by that. Again, we have a stable part that I'm highlighting right now, and then we have a part that's going to be changing, usually by 1, hopefully. Okay, that's going to be our recursive call portion. So our complete solution for this is our base case was a to the 0 equals 1, and then anything that's greater than 1 for its overall solution, and remember n is, then we're going to go ahead and do our a plus 1 equals our a times n. That's our recursive portion of it in order to be able to do this. So that's part 1. Here's our example number 2. We're using a sequence. Go figure. Where a of n is going to equal, well, the n portion is going to be, frankly, a positive integer. So we have a formula that's going to create that sequence. A of n equals 2n plus 1. Now, there's not a lot to translate, to be honest, on this one, but remember, we'll start at n is equal to 0 for our base case, and then we'll move into 1 and up for the recursive case from there. So take care of the base case first. We're going to have a of 0, there's where my 0 comes from, and then 2 times 0 is plus 1, which equals 1, which that part hopefully is pretty easy to figure out. So that's our base case. Then we start looking at the recursive pattern in the recursive case, just like we did before. Now notice again, I'm putting a of 0 in there just to kind of help out with the overall pattern. A of 1 is going to be 2 times 1 plus 1 equals 3, and then you can kind of see, by the way, you'll notice that we're constantly adding 2 to our next sequence in the set that we're creating for this particular problem, or sequence in this particular problem. So this is how this would work out. We have a of n equals a of n minus 1 plus 2. So that means for a of 4, I would get whatever a of 3 was, which was 7, and I'm going to add 2 more to it to go ahead and get 9. So that's how that overall equation works out. Now again, notice that's a recursive case, isn't it? Number 1 is greater than 1, and then number 2, we have our part that's stabilized, and we have our recursive portion of that call that's going to frankly change because it's an n minus 1. So our complete solution is set up below, but all I'm doing is pulling from the base case and our recursive case.